All right, we'll do that next. To begin with, let's finish up chapter 4. We only have 2 more sections, and then we have chapter 5, and then we're done for the semester. Where did we leave off? We left off using, learn how to graph using the first and second derivatives.
We're in
Now,
section 6.
yes, we're chapter 4, section 6. Which we the probably problems we call optimization problems. Now, the reason we call them optimization problems is because in these examples, we'll be looking for at equations examples where we're looking at what is the most successful, what is the least effective, what is the most productive or least cost efficient. So we'll be looking at extremes. Unfortunately, these are all going to be word problems, which we have to review from algebra. How do we solve word problems? When you read the problem, identify the dependent and independent variables. Do not work. Also identify what it is asking. If you have to, like if it's motion problems, draw a picture, a diagram, something so you see the relationship of your variables. Identify the variables and their relationship. To each other. Identify the formula or equation that you will need. Work out the problem. And test your solution. This is the check your answer part. So again, because these are all going to be word problems that deal with movement, motion, construction, destruction, or whatever, we're going to have to identify all these parts. We're back to algebra. So let's look at an example. Hey, don't worry, summarize it best you can. Example 1. An open top box is to be made by cutting small congruent squares from the corners of a 12 by 12-inch sheet of tin. And bending up the sides. So the question is, how large should the square cut be taken from the corners? All right. First sentence is telling us what? Which is what? Right. An open top box.
Just like geometry.
More like algebra. All right. So we have, but this box is cut from one sheet of tin that's 12 inches by 12 inches. What you have to do is you have to cut these corners, and they all have to be the same size to get what? Okay, I didn't put this, yeah. How large the box should be cut, taken from the corners to make a box hold as much as possible. There. So that's, so remember, this is this is an optimization problem. So since it says holding as much as possible, so we're looking for the maximum. So what sizes should these cuts be to give us the greatest size box? What else do we know from this statement? I know it's stuff that's not there, that's really there. It's looking for what? The stuff inside the box. What is that called? Volume. So we know we're dealing with a volume. What's the formula for volume? Okay, we have the length, we have the width, and we have the height. Great, two equations. Because if you think about it, a volume of a box, well, open-end box, length times width is actually what? So that's really what we're looking at, is the area of the base, because we only have one bottom, and then the height. We're looking at really two separate parts. So the question is, how do we go from this picture to this formula? What do we know? We know the height. What of these are gonna be the heights? Yeah, these are the x's, because once we finish, we bend them up. So our height is the x. So once we finish those, we bend these here, and then we have the sides of our box. Now we gotta figure out what formula do we use for the area. Fortunately, the area, since it's a square sheet, is gonna be the same. So what is this length here? No, it could be, has to be.
Must be less than 12. Say like y squared or something like that.
No, but it has to be less than 12, true. Yes, yes, okay, yeah, but we know what L is. What's L? Yeah, so this is gonna be 12 inches minus the two x's. Very good, yes. Now I gotta put that together. Since this is a square box, it'll be the same there too. So the area is 12 minus 2x squared. One of these days, I'm gonna have my class, instead of having this example like this, I'm gonna give you all a piece of paper and say, create the box that holds the most. And I'll figure out how to do it. Okay, so we have that. How do we go about finding, what are we finding now? We have this much information. What are we looking for? Yes. How? We're looking for a max. So yes, we're looking for a vertex. Only thing about it is a volume is cubic function. Aren't cubic functions graphs like this? What's that? Right, because this is gonna make it squared, times it makes it a cubic function. Isn't that gonna be a problem? Actually, no, actually, good idea, but no. But think about it. This is a cubic function if x is positive. If we expanded this one, what would this give us? 12 times 12 is 144. I read between lines. 12 times -2, negative 24x. Negative and positive is negative. 12 times 2 is 24x. Negative and negative makes it a positive. 2 times 2 is 4, x squared. Now distribute that. We get 4x cubed. These two make it 48x squared. plus 144x. So we have that so far. Now what do we do with it? We're looking for a maximum, a vertex, as you said. How do we find the vertex? If we set it equal to 0, that's a good question. If we set this equal to 0, what would we find? Let's do that. If we set v equals to 0, what's that going to find for us? Which we're going to have to do that anyway for checks and balance. And it's going to slap you when you hear it. Well, let's go ahead. Let's solve this for 0. Let's see what we get. X 12 minus 2x squared. If we set those equal to 0, we get x equals 0. And then all we have to do is set the middle inside there equal to 0. Work it out. See what you get. And what do you think those represent? So we have x equals 0. That's one of them. What's this one going to give us? That tells us our domain. Whatever answers we get have to be between there. Because if we think about it, at 0 and at 6, that's when our graph is going to be on the x-intercept. So somewhere between these two, our vertex lies somewhere between there. So that we have to start with that to see what are we dealing with. Now we have this. What do we do next? And then do what with that? You're on the right path. Because this is the first derivative is a what? First derivative is a slope. How do we know we have the vertex? Slope is equal to 0. So we set first derivative equal to 0 and solve from there. What do they all have in common? They all have a factor of 12, right? How many times does 12 go into 96? 8 times. 12 goes to 144 12 times. Because the degree of our vertex, or our first derivative is 2, we have 2 answers. So we're solving for x. The second sign's a plus. That tells us the signs are the same. They're both going to be minuses. Take the leading term, leading numbers. So we have 1 times 12 equals 12. What two numbers multiply together to equal 12? When I add them, it equals 8. Six and 2. It doesn't matter where they go. Remember, we've set this equal to 0. So by the zero product principle, we got to find out what our values are, what our zeros are. These are our zeros, our critical values in this case, because they're called zeros because I plug them back into the first derivative equals 0, which means it's also where the slope is 0. So those are my critical values. But what do we know about one of them? Well, we remember we said that our domain was between 0 and 6. It goes up, it goes down. That means we can have a bounce like this. But again, we're just looking for this part. We don't know what happens outside that person. How many vertices, how many solutions will this equation have? It's a cubic function, so it has 3 solutions. So 3x intercepts. We simply found 2 of them. There's one more left somewhere. Or we could have a multiplicity of 2. So we have to use this one. At 2, we have a vertex. Now what do we do? With those values, what do we do? And do what?
So we plug in 2 for our
But there's one thing we did earlier in the chapter, we talked about whatever we do with testing your maximum minima. Whenever you test your maximum minima, you always have to get 3 points, at least 3 points. You have to test it at the endpoints. And since C is somewhere between there, you have to test it at C point also. So we have to test it at 2 or at 0, at 2, and at 6. Our domain is 0 to 6, and our vertex at 2. So if we plug in 0 for our original equation, which is this one here, if we plug in 0 there, what do we get? Yeah, but 0 times anything is 0. If we plug in 6, what do we get? Well, it's remember we got as our intercepts. 2 times 6 is 12. 12 minus 12 is 0, so the whole thing's 0. Now if we plug in a 2 in there, I missed that, sorry. 4, 12 minus 4 is 8. 8 squared is 64, so it's 128. So the maximum air volume we'll have, is x equals 2. So our box will be 2 inches high, 8 inches long, and 8 inches wide. That's going to hold the most. So far, so straightforward. Okay. Now let's change it. Boxes are easy. Boxes are fun. That's how come we make boxes. Whenever we ship things, even though it's a lamp or any object, we always put it in a square rectangular box because they're easy to build. They're cheap to design. What if you worked for a soft drink industry? You were asked to design a 1 liter can shaped like a right circular cylinder. What dimensions will use the least amount of material? Pretty short sentence for asking a lot. First sentence, you were asked to design a 1 liter can shaped like a right circular cylinder. What does that mean? What is right? Why is that in there? 90 degrees, exactly. I mean, who the hell would build one that's not 90 degrees? So that again, it has to be stated. If it's not stated, you can design it however you want to. So it's got to be a right circular cylinder. What dimensions will use the least amount of material? Pretty straightforward, but what do we need to know? First off, since we're dealing with what's inside there, we need to know how much stuff, liquid or something will be in there. Well, what is 1 liter? Yes, it's a volume, but how do we, because we're looking for, we have to go from liquid measurements to length measurements. That's the beautiful thing about metrics. We can't do that in American systems. So 1 liter is equal to 1,000 cubic centimeters. Now, where did that come from? You hear it all the time on TV shows, and whenever a doctor asks for a syringe or a shot, they always says, give me 3 cc's. That, again, what, if you think about it,
For an example, in 3 C's.
well, I'm saying there, you have a shot. It's a hypodermic,
Of an injection.
and inside there is a liquid. And it says cc. What does cc stand for? Cubic centimeter. Meter, centimeter of liquid. That's always been fascinating to me. But again, everybody else just goes over their head. Oh, okay, great. But that's super important. So we have to know this conversion because that's going to be very important because now we're dealing with measurements of length of some sort. So how do we go about doing this?
Formula for a cylinder.
What's the formula for cylinder? Are we looking for volumes or no, you don't need that. Are we looking for volumes or area?
Well, you have a volume.
We have the volume. Now we have to get, but we do have to find the area. Why do we have to find the area? Of what? Think about it. If you have a cylindrical can, it's hollow inside there, isn't it? So if you think about it, what is it made up of? 3 parts. What are the parts?
Top and bottom, which are the same.
Mm-hmm. All that together, let's put it together and create a can that will hold 1 liter, which is why we need to know the centimeters for all this other stuff. So what's the formula for circles? This is the area because we're looking for the, just the stuff inside there. So what's the area of a circle? Pi r squared. And you think about it. 2 pi r is the distance from around a circle. That's circumference. Where did 2 pi r come from? It's the derivative of the area. Again, just side note, free of charge. So we have 2 of those. How about the sheet of paper? Okay, we'll start with there. Or height. We'll do height. How do we go about finding the length?
What did we get, that's the circumference of the circle.
Yes. So we could just say, so it's 2 pi r h. Because the length here is the distance around the circle, which is 2 pi r, which is what you said, times the length, times the height. Now we gotta start putting this stuff together. So the volume, it has to be 1 liter. What's the formula for it? What's the volume formula? It's the area of the circle. It's the area of the circle times the height. So the volume of this can is the area times height. Look familiar? We just did one a second ago with the box. And this has to equal what? Cm cubed. So we know we have pi r squared h has to equal 1,000. So let's now start putting all this stuff together, because now we have to look for specific values. Eventually, h is going to be the only, h will be the variable that we will be looking for the most. Why? Because it's in both of these that we could really work with. R has too many of them. R is squared here. R is by itself there. So we're not going to mess with R. We're going to mess with H. So the area formula here. So we have the area formula here. We have this formula here. Let's solve for H. That's the only thing that's the outlier in those 2 equations. So what is H? Divide both sides by pi r squared. So here's my H formula. So my area becomes 2 pi r squared plus 2 pi r 1,000 over pi r squared. simplify this algebraically, the pi cancels, one of the r's cancel. So 2 times 1,000 is 2,000 over r. So now this is my new area formula. We had to get rid of h. Why? Because the function is now going to be relative to the variable r only. And we couldn't do it with h in there because this one didn't have an h. So what do we do with this equation now? What's the formula looking for? Least amount of material. We're looking for the minimum. Minimum of what? This will help us find the minimum of this function, because then we'll solve, once we find the minimum of that, that'll give us the r value, that'll give us the lowest value of that equation. So we have to find a prime. A is equal to so what's a prime going to be? Now I'm going to take the derivative of this one. So it's going to be minus 2,000 over r squared. Set it equal to 0. So we get 2,000 over r squared, 4 pi r. We're solving for r. Multiply both sides by r squared. R cubed divided by 4 pi. So r cubed is equal to 500. Take the cube root of both sides. So the minimum will happen when r is that, whatever that value is. What do y'all think? I'm gonna calculate it. Let's see. Oh, let me do my computer here. I can get my calculator here. No, it doesn't have it, so I'll put it on my Excel. So we have
Mutual that in Excel.
4 to the power 1/3. Yes. You can put equal sign first, so that tells you it's an equation. 500 divided by 3.14 to the power 1/3. Yeah, because it doesn't have a cube root function. So this will be something like 53.08 or 53 centimeters. Or 5.3, I should say. Yeah, I put I put a wrong number in there. I just noticed that my numbers are pretty small. Yes. So 5 point what?
5.419.
Yeah, so that's the radius in centimeters. So what would that make my height? Or 4.2, make it 4.2. So the height, we know the radius is radius is 5.42 centimeters. And the height, remember the formula for our height? Was 1,000 divided by pi r squared. .14, 5.42 squared. Approximately 10.85 centimeters. Why is it centimeters?
So it was like a metric and that was the only system that would convert.
Oh, yeah, because the only thing we had that could convert with, where I put that? Yeah, right here. Because the volume from 1 liter equals 1,000 centimeters. We did that conversion because we couldn't leave it in liters. How would you cut a metal piece in liters? So that's why we converted to distance. Again, it's always been fascinating to me. Example 3. A rectangle is to be inscribed in a semicircle of radius 2. What is the largest area the rectangle can have? And what are its dimensions? Well, that's a lot of words. Again, we have to understand what the words are telling us. In the first sentence, a rectangle is, what does inscribed mean? Written inside, yes. Inside a semicircle. What is a semicircle? By definition, yeah, half a circle. So we have half a circle. Actually, we do it like this. Why? Because the radius of this semicircle is 2, which means I go up 2, I go out 2, and I go out to -2. I can do it that way easier. And a rectangle is supposed to be inscribed in there. We don't know what these X's are. What is the largest area of the rectangle? So the area of the rectangle is base times height. And what are its dimensions? What are B and H? So basically, that's all we're asked to find. What are we given? So this rectangle, the base is how far? 2x. 1, 2. What else do we know? We know the area formula. The area formula is based on, well, we know the basic formula. What's the height? What's the height of that? Of the rectangle? The height is here. It's got to touch that semicircle. What's the formula for semicircle? The formula for a circle is x squared plus y squared equals r squared. Or if you wanted to, x minus h squared plus y minus k squared equals r squared. H and k is the center. And that's at the origin, which is 0, 0. So we have x squared plus y squared equals r squared. So what's the radius? Radius is 2. So x squared minus y squared equals 2 squared. We want to solve for y. So we have x squared minus 2 squared equals y squared. I move this one over and that one over there. I'm solving for y. Then I do what? That's the height. Oops. Yeah, that's the height. It's the y value, the height. So the area is base times height. So that two x times square root of x squared minus 4. That's the formula we'll be dealing with a lot. Remember what I said, the 5 steps. Read the question, get the pieces you need, tell them how they're related, and find the formulas you need. The hard part about this, there is no formula given in the sentence, in the paragraph. You have to extrapolate all that stuff from there, from what's being asked. So how do I go about setting this up? What am I really looking for here? We know my domain. What's the domain? We could look at from -2 to 2. Let's just keep it simple. Let's keep it from +2 to 0 to 2. Let's keep it in the first quadrant. Yeah. All right. So since we're looking for the largest area, how do we find the largest area? It has to be within a domain, right? So yeah, it's a maxima. So what do we use to find maxima and minima? Maxima, minima are extrema. Extrema are found how? First derivative, right? Unfortunately, we have a product rule here. A little bit more than that, because this is going to be 2x. This is going to be x squared minus 4 to the power 1/2. So the derivative of 2x is 2. The derivative of this, we use a chain rule. Times 2x. So 8 prime will equal 2 times the square root of x squared minus 4 plus 2x over 2 square root of x squared minus 4. 2's cancel. So what do we do now? Yes.
Get the. Root of x squared minus the bottom, those are simply, because it's a negative 1/2 exponent, it drops it down and puts it under a square root.
Right, yeah. Because this right here is negative, it goes on the bottom. And this 1/2, since it goes on the bottom with that 1/2. So it would be 1/2 times that. Times 2x. Oops, hold it. I got that. So I have times 2x. Was this times this. I forgot about that 2x there. So we set this equal to 0. Actually, before that, well, we set it equal to 0. Get rid of the fractions. How do we get rid of the fractions? Whenever you have fractions in the equal sign, to get rid of the fraction, find the LCD. The LCD in this case is simply the radical. Multiply it to each term. So we have radical x squared minus 4 times 0. Radical x squared minus 4 times 2 radical x squared minus 4 plus radical x squared minus 4 times 2x squared over radical x squared minus 4. This is where you get rid of the fractions. Anything times 0 is 0. Now we multiply. Get rid of the parentheses. Radical times radical is x squared minus 4 plus 2x squared. Just get rid of parentheses, so it's 2x squared minus 8 plus 2x squared. Combine like terms. Move the 8 to the other side. Divide by 4. So x squared equals 2. X equals plus or minus square root of 2.
Recommended 0 to 2,
Right. We don't use the negative one. This is above our domain. So that's our critical point. Critical value. What do we do with it? Plug it in where? Right. Right. So we for the area of original equation was that one. So the area was 2x times radical x squared minus 4. 2 times radical 2 squared minus 4. Square root of 2 is cancel. This part here, I did it backwards. When we did our area originally, right here. Because here's this is where I messed up right here. I changed the sign by mistake. It should have been, it's not much of a change. It should have been y squared equals r squared minus x squared. So y should have been square root of 4 minus x squared. So y should equal 4 minus x squared. And that's, I mean, it's not going to change anything else. So 4 minus 2. 2 radical 2 radical 2. 2 times 2 equals 4. Radical 2 is radical 4. Equals 2. Okay, this is only one of them. Remember, we're supposed to 3 points. What are the end of our bounds? Our domain was 0 to 2. If we take a to the 0, we get 0. We get a to the power 2, a to 2, we also get 0. Why is a to the 0? Why is it 0? 2 times 0 is 0. If it's 2, 2 squared is 4. 4 minus 4 is 0. So the endpoints are going to cancel out. So radical 2 is our value of whatever we're looking for here is the height. So the height was, where's our height? What am I looking for here? So radical 2 was the height. And the base was 2 radical 2. Any questions about that? The rest of the stuff, any problem doing the rest of the stuff? We had to follow through with the answers here. And because the area, we figure out, no, the area is 4. And the base times height.
Wait, so how did you get 4 square root of 2 and 2 square root of 2?
For what? That's not 4. That's just
Oh,
height is
okay.
just,
Okay.
because height's what we're looking for. And then the base was, the formula for it was 2x.
Mm-hmm. Okay.
That. And the height was what we're originally looking for. Let's skip that one. Oh, economics, because we're running out of time. I want to cover the other method. And we'll do economics also. So far, when we've always done physics or motion or construction problems when we deal with calculus. In business, whenever we deal with rates of change in business, whenever we say marginal, that's a rate of change. Why is that important? What is profit in business? How do you calculate profit? Minus cost, right? Revenue minus cost. What's that?
The percentage of your market.
Yes. But now margins and marginal are a little bit different. Marginal, so let's say our revenue was a function, well, let's look at this next, first example. Our revenue was determined by 9x. Because revenue is dependent on amount of sales. X is the amount of sales. Cost of this example was x cubed minus 6x squared plus 15x. It cost you this much to create one bit of object. And your revenues, you sold 9 of those. So the profit would be the revenue minus the cost. Okay, so suppose this is this. Here's a question. Example 9. Is there a production level that maximizes profit? If so, what is it? That's all the question said. It gave us this information. It gave us the R equals this and C equals this. Is there a production level that will maximize profit? So how do we figure out production of what? Of X's, yes. We have to look for how many X's do we have to create to maximize profit. Again, maximize, it's a maxima, minima, it's an extrema. So profit is equal to revenue minus cost. . At break-even point, what do we have at break-even point? At break-even, that's when revenue equals cost. Which is, yeah, zero, because you're not making money, you're not losing money. So that's where we're gonna start off with. So let's see what we have here. We have 9x equals, what's the formula? 3x squared minus 12x plus 15. Take the derivative of these, because now we're looking for the marginal revenue equals the marginal cost.
The derivative of 9x.
Yes. Then 6x minus 12. Oh. I did the ruse. It was x cubed 12x. I'm sorry. I was looking at the wrong piece. 9x equals x cubed minus 6x squared plus 15x. So 9 equals 3x squared minus 12x plus 15. Now it's quadratic. So what do we do with that? Subtract 9 from both sides, because we want to set it equals 0. We need to know what my values are for the R. 12x. 15 minus 9 is positive 6. Let's hope they're integers. So take the first term and the last term. 3 times 6 is 18. So what two numbers multiply to equal 18? When you add them, equal 12. Or is there one? 6 times 2, that won't work. 6 times 3, that's 9. 9 times 2 is 11. So we can't factor. What do we have to use then if we can't factor? We either use complete the square or we can use the quadratic formula. So let's use the quadratic formula. 3x squared minus 12x plus 6. Solving for x, a is 3, b is negative 12, c is 6. Negative b plus or minus b squared minus 4ac over 2a. Negative 12, negative 12 squared minus 4 times 3 times 6, 2 times 3. Negative is a positive 12 plus or minus 144 minus 12 times 6. Over 6. 12, so x is equal to 12 plus or minus 144 minus 72 is 72 over 6. $36. So that means square root of 72 is made up of 6 times 6 times 2. So the 6 comes out in front. factor out of 6. So x is equal to 2 plus or minus square root of 2. Same stuff we did in algebra many years ago. So my calculation is 2 plus square root of 2. Where's my square root of 2? Two plus is 3.4142. Here. My clear button. So I have 2 minus square root of 2. 0.586. So those are the two possible production levels of my object. And I'm looking for what? Maximize profit. So to maximize profit, I gotta do that to both of them with 3.4 and 4.56. And which is going to give me the most? Actually, is there another way we can do that? Since we're looking for the maximum minimum, do we know any functions, any operations that we dealt with calculus that'll tell us if it's going to be a maximum or minimum? No. What's okay? First derivative will find us what? Simply the extrema, which we did that. What's second derivative going to find for us?
Point of
Second
inflection
derivative, what's that?
or point of inflection?
Yes, if we set it equal to 0, if we take the second derivative and set it equal to 0, that finds us a point of inflection. Now, from that point, we can take let's say that x equals 0. If we take a point to the left of it and a point to the right of it, if we put it into our second derivative and it's positive, what does that tell us? It's concave up, so we have a minimum. If we put the second derivative, we put our point to the right of it, and it's negative, that means it's concave down, so we have a maximum. So that's our next step, is do the second derivative of the p. So the derivative of r was 9. The derivative of c was 3x squared minus 12x plus 15. So that gives us 9 minus 3x squared plus 12x minus 15, negative 3x squared plus 12x minus 6. Take the second derivative, we get negative 6x plus 12, set it equal to 0, x equals 2. So fortunately, if x equals 2, this is our point of inflection. All we have to do now is plug in both of these into our second derivative, which is much shorter. It's a smaller equation. So our second derivative was negative 6x plus 12. And our possible x values were 3.414 and 0.586. (3.414) negative 6 times 3.414 plus 12 0.586. Six times 0.586 is going to give us something like negative 3. 6 times 3 is 18. So this one's going to be negative. This one's going to be positive. So if the second derivative is negative, what does that tell us? Concave what? If it's positive, it's concave up. So our maximum will occur at that x value. Maximum loss. Yeah, this is the loss we're looking for here. This is our profit. Remember, this is our profit statement. So we want the lowest part, that's the maximum loss. Because the maximum profit is here, maximum loss is here. So, or you have the minimum losses there. What's the next one? Maximum loss at that max prof at that's how you read these tables. So the maximum profit occurred at 3.14, the maximum loss occurred at 0.586. And it wanted maximum profit. So max profit at x equals 3.414.
Company is me.
Whatever the objects are they're making, right? They'll maximize their profit if they do that. Okay,